I'm going to start just like a minute and a half early because I wanted to talk about this briefly, and we're kind of a little bit compressed for other things. This hit the headlines yesterday or the day before. There's a study published in the Proceedings of the National Academy of Science that says that they have evidence that human evolution is continuing. This is coming from the Framingham Heart Study. And this has medical histories of 14,000 residents of Framingham, Massachusetts since the middle of the 1900s. They've looked at a lot of things, including people's height, weight, the number of kids they had, so forth and so on. And this article, the punchline that's getting picked up in the headlines is the following, that if these trends were to continue with no cultural changes in the town for the next 10 generations, by 2409, the average Framingham woman would be 2 centimeters shorter, 1 kilogram heavier, and have a healthier heart. Have her first chart. Okay. Does this give you a little bit of pause? Yeah. Okay. So they're looking at, I haven't had a chance to look at the whole PNAS study because it wasn't online yesterday. It came up this morning, and I haven't had a chance to digest the whole thing. But it's over here. If you search for one of the authors' name, Eubank, E-W-B-A-N-K, and PNAS, you'll be able to find the study. Here's what the top of it looks like. So Byers, Eubank, et cetera. All right. So what do? They sort of, in broad stroke, they look at the fecundity of women, how many kids they have, and other aspects of their physiology, how much they weigh, how tall they are, et cetera, and find that sort of women who are a little bit stouter tend to have more kids. And of course, some of these things are inheritable traits. And so the conclusion is that over time, you're going to see shorter, heavier women in this town, so that by the time another 400 years has gone by, there's going to be about a 2 centimeter difference, a little less, 3/4 of an inch, roughly. Okay, somebody want to raise some, so we haven't really talked about it in detail, but there's this notion of confounding, which means that two different things can have the same apparent effect, and as a result, it's very difficult to tell them apart in the data. So can you think of some things that might be confounded in this study with sort of the genetic effects on height, weight, et cetera, fecundity? Let me just, first of all, I don't know how they dealt with it, but you are aware that an awful lot of women say, gosh, I just never could lose that last 5 or 10 pounds after I had my baby, right? Okay, so that's very different from weighing 5 or 10 pounds more before you had your baby, yes? So that would be an issue that they need to pay a lot of attention to. Are they looking at people's weight? They're looking at postmenopausal women. So these are women who are now done having kids, and they're looking at their heights and weights. They would need to know a lot about their history to know whether they were heavier and shorter before having their babies or only afterwards, okay? Now, if you're comparing them to other women in the population, there are a number of effects that you might see. So first of all, if you don't have kids, do you have more time to spend at the gym or less time to spend at the gym? Okay. If you are really, really concerned about your physical fitness, so forth and so on, might that be a factor that influences your decision to have kids? Yes. Okay. There's all kinds of things going on here that could be confounded with the effect that they're claiming to find. I haven't had a chance to look in detail at what they did, but it looks like most of it is based on modeling that involves assumptions that are far-fetched, if not absurd. So at any rate, I encourage you to look at this stuff and try to think it through, and maybe we can have some discussion on the email list about this, but it's an interesting use of statistics. There was some, a flurry of email last night starting around, I don't know, 9 o'clock or something like that, relating to the homework. I really encourage people to start the homework a little bit earlier and to come to office hours. And I understand that the webcast hadn't been posted from last Thursday then, so you didn't have that to return to for a review. But this issue of conditional probability involving card hands and whatnot, the key idea is to understand what it means for a deck of cards to be shuffled well. If you understand what it means for a deck of cards to be shuffled well, everything else is just really, really clear. Okay, what does it mean for a deck of cards to be shuffled well? Every card has the same chance of being in any place. Every ordering of the deck has the same probability. So if every ordering of the deck has the same probability, it's just as likely that the ace of spades ends up being the top card, as it ends up being the 17th card, as it ends up being the 23rd card, as it ends up being the 52nd card, right? Because every ordering of the deck is equally likely. That ace of spades is equally likely to show up anywhere. Does that make sense? Okay, so conditional probability, anyway, so it's just what it means to be well shuffled is that the ordering of the deck has the uniform distribution on permutations of the deck, all 52 factorial permutations. Equivalently, every ordering of the deck is equally likely. All right, we talked last time about the Monty Hall problem, the let's make a deal problem. I'm going to close the door. And we had some arguments, intuitive arguments, arguments involving conditional probability, et cetera. And now what I want to look at is, could we collect data to decide between the two situations? And in order to use the data to decide between the two situations, we have to think through the probability a little bit more. This is going to give us an opportunity to introduce at least half a dozen concepts that we're going to use from now till the end of the term. There's a lot of stuff in this chapter. So let's see if we can make sense of it. So we have two scenarios. Under one hypothesis, there's no advantage to switching when the host shows you that the prize isn't behind door 2, for the sake of argument. So we're back in the Monty Hall problem. 3 doors, prize is hidden behind 1 door. You pick door 1, door A. The host shows you the prize isn't behind door B. Should you switch or not? One group of arguments says, doesn't matter whether you switch. The chance of winning if you switch is 50%. Might as well stick with your original guess. The other argument says you should switch. The chance of winning if you switch is 2/3, whereas it's only 1/3 if you stick with your original guess. Therefore, you should switch. Okay? So if the first argument is right, then whether you win by switching, oops, how about putting 1 on one of these? Whether you win by switching is like whether you get a ticket labeled 1. If you have a box of tickets, there's 1 ticket labeled 0, 1 ticket labeled 1, you stir them up really, really well, you reach in without looking, you pull out a ticket. If the ticket is 1, you won the game. Okay? If it makes no difference whether you switch or not, then if you switch, the probability that you win is like the probability that you pull the ticket labeled 1 out of this box. Okay? This is called a box model. We're trying to make a model that is probabilistically equivalent to some other situation, but that involves drawing tickets out of a box instead. So this is a sort of a canonical thing. And if the other hypothesis is right, then when you switch, it's like reaching into a box that has 2 tickets labeled 1 and 1 ticket labeled 0. You stir them up really well. You pull out a ticket. If you get the ticket labeled 1, that's like winning the game. Okay? So this corresponds to the hypothesis that you do better by switching. You have a 2/3 chance of winning if you switch. This corresponds to the hypothesis that it makes no difference whether you switch. You have a 50% chance of winning if you switch. Okay? Now, let's imagine playing the game a bunch of times. So let's think about playing the game 50 times, just to be concrete. So we can imagine we stir the tickets up, we reach in, we pull out a ticket, we write down whether we get a 0 or a 1. We put the ticket back, stir it up, reach in, pull out a ticket. So if we do it over and over and over again, in which of these scenarios are we likely to get more tickets labeled 1? Left, right? Okay. So if you're more likely to win by switching, you're more likely to win more times in 50 plays. than if you're equally likely to win. Okay. All right. So we could have a rule that says, I'm trying to figure out which of these two situations is real, which is reality and which is a fallacy. And my rule could be, I'm going to play the game 50 times. I'm going to reach into this thing 50 times, stir it up, look at the ticket, replace it, so forth and so on. And I'm going to count how many times I win. And if I win a lot of times, I'm going to conclude that this is reality. And if I win not so many times, I'm going to conclude that this is reality. All right? So we want to figure out where to draw the line between a lot of times and fewer times, right? How many times, where should we draw the line so that if we get that many or more wins in 50 plays, we should conclude that this is the box that we were drawing from. That is, that it's better to win, better to switch. Or if we get less than that threshold, we conclude that this is the box we were drawing from. That is, it makes no difference whether we switch or not. So far, everybody with me? Yep. Question?
So we're basically trying to find out what is the lowest threshold that we can have of wins on one or the other?
Okay, let me go a little bit further, and maybe this will be clear. So we're trying to pick a threshold so that if the number of wins is bigger than that threshold, if the number of tickets labeled 1 is bigger than that threshold, we're going to conclude that this is what's really going on. Now, we've already reasoned through. We believe this is what's really going on. We have theoretical arguments that this is what's going on. But we're backing up and pretending that we didn't. We're developing some other theory where we would do an empirical test. So we'd actually play the game and look at what happens. All right. Now, any rule for making a decision that this is the right box or this is the right box can make mistakes, right? Because with either of these, you could get no wins at all, 1 win, 2 wins, on up to 50 wins in 50 plays of the game, right? They have the same possible outcomes, but those outcomes have different probabilities. Okay, so if we have a rule that says, conclude that this is the box you're drawing from if you get 29 or more wins in 50 plays of the game, there is a chance you would get 29 or more wins even if you're drawing from this box, right? If you're drawing from this box and that happens, you would make the wrong decision. You would conclude that you're drawing from this box and be wrong. Conversely, if we set the threshold at 29 wins, getting 29 tickets labeled 1, then even with this box, there's some probability that we would get fewer than 29 tickets labeled 1 in 50 draws from the box. And so we could erroneously conclude that we're drawing from this box even if we're drawing from this box. There's 2 kinds of mistakes we can make. We're going to get into this in a lot more detail when we talk about hypothesis testing, but generally in trying to decide between 2 states of the world, there's 2 kinds of mistake you can make. Reality can be like this, and you can erroneously conclude that it's like this, or reality can be like this, and you can erroneously conclude that it's like this. We're going to want to look at the chance of each of those kinds of errors. So we're going to pick a threshold, and then we're going to look at what's the chance that we make one kind of mistake, what's the chance we make the other kind of mistake. So to find the chance we make the mistake, it's going to be the chance that if reality is this, we erroneously conclude it's this, and the chance that if reality is this, we erroneously conclude that it's that. So we don't know what the chance is that reality is this or that reality is that. We only know what's the chance of making a mistake on the assumption that reality goes one way rather than the other. Okay? All right, so it's clear to everybody that if I draw 50 times from this box, I'm likely to get a larger number of tickets than if I draw 50 times from this box. A larger number of tickets labeled 1 than if I draw 50 times from this box, right? Okay, so let's look at what happens. So this applet is one that you're going to see over and over and over again. And this represents the box of tickets. This has 1 ticket labeled 0 and 1 ticket labeled 1. And when we press the Take Sample button, this is going to draw 50 tickets out of the box with replacement. Okay? So this is going to say, if reality were this box, this corresponds to playing the game 50 times and seeing what happens. Okay? The average of the box, that's the average of these ticket labels. The average of 0 and 1 is a half. The SD of the box, the standard deviation of a list of tickets, one of which is 0, one of which is 1, is 0.5. We'll talk about expected values, standard error, so forth later on. At the moment, you can track that we haven't drawn any samples yet. All right, so let's press the button. Okay, that time we happen to get exactly 25 wins. Okay, exactly 25 tickets labeled 1 when we drew from the box. Did that have to happen? No, it's random, right? You reach in, you might not get 25. So here's second time. This time we got 24. We just played the game again 50 times. We just played the game 50 times again. We got 24 again. So this is a histogram of the outcomes. This is twice as tall as this because we've seen the outcome 24 twice, and we've seen the outcome 25 once. Keep going. That time we got 20. Okay. So we can do this, and we play the game over and over again, and look at the distribution of outcomes that we get. Now let's speed this up. So now we're going to play the game 1,000 times. 2,000, 3,000. Okay, we've now played the game 10,000 times. And you can see that sort of on average, you win about 25 times. But there's some spread to that, right? There's still a reasonable fraction of the time you win 30 or more times. Let's look at the empirical frequency with which you win 29 and a half or more times. Okay, so in these trials, 9.5% of the time we got 30 or more wins by switching. That is, we got 30 or more tickets labeled 1 when we drew from the box. So far, so good? Okay. So what we'd like to do, the next step we're going to do is to figure out what is the actual probability distribution of the number. This was sort of an empirical experiment, a computer experiment, to sort of see what's typical range, so forth and so on. But we can actually calculate what is the probability that you would get exactly 25 tickets labeled 1 when you reach into this box and pull out a ticket 25 times with replacement, stirring it up each time, doing it independently. So the draws are independent. Each of the 50 draws is independent of the rest. And okay, so how do we do that? So what, for the sake of argument, is the probability that we get exactly 25 tickets labeled 1 in this experiment if we're drawing from that box that has 1 ticket labeled 0, 1 ticket labeled 1? How do we get started? We've got 50 draws. What's the chance that the first draw gives me a ticket labeled 1? Okay, a half, right? Yep. What's the chance the second draw gives me a ticket labeled 1? Okay, the draws are independent, right? Okay, so this probability the second draw gives me a ticket labeled 1 is the same as the conditional probability that the second draw gives me a ticket labeled 1 given that the first gives me a ticket labeled 1 or given that the first gives me a ticket labeled 0. The draws are independent of each other, right? Okay, so if I wanted to come up with one particular way of getting 25 tickets labeled 1 and 25 tickets labeled 0 in the 50 draws, I could say that, say, the first 25 give me the tickets labeled 1, and then the second 25 give me tickets labeled 0, for instance. That's one way that it could happen. I could get 1s 25 times in a row, and then 0s 25 times in a row. Okay? What's the probability of getting 25 1s in that particular way? So each of these, so the chance that I get a ticket labeled 1, each of those contributes a factor of a half, et cetera. What's the chance I get a ticket labeled 0 on the 26th draw? A half, et cetera, right? So I get 25 factors of a half and then another 25 factors of a half. So the chance I get 25 tickets labeled 1 and 25 labeled 0 in this particular order is a half to the 25th. Okay? We're using the independence of the draws here, using the fact the chance of getting a ticket labeled 1 is the same as the chance of a ticket labeled 0 because there's 1 1 and 1 0 in the box. Okay? But this is only one way in which I could get 25 tickets labeled 1, right? I could get first 24 ones, and then a 0, and then the 26th a 1, and then the rest zeros. I could get the last 25 ones and the first 25 zeros. I could get the first 2 ones, then the next 2 zeros, etc. Right? How many ways are there of getting 25 tickets labeled 1 and 25 tickets labeled 0? There's 50 places in all. What do I need to specify a particular sequence of zeros and ones? Here I said the first 25 get ones, the last 25 get zeros. I basically need to say which of these get ones and which of them get zeros, right? From the 50 places, I have to decide which 25 get ones. How many ways are there of deciding which 25 of 50 things you put ones in? 50 choose 25, right? From the 50 places, you pick 25 into which to put ones. So I'm going to write 50 choose 25 here, but then I'm going to ask one question. Can I just multiply by that? Does that give me the probability that I get 25 ones and 25 zeros? What am I implicitly assuming here? What am I relying on? Yeah. The last 25 are all zeros? Well, I'm saying I'm going to put ones in 25 of the 50 places. The other 25 are going to get zeros. Yes?
That you're relying on the fact that it's going to be split exactly in half?
Well, I'm computing the chance that it's split exactly in half. So I'm not relying on that. That's what I'm trying to figure out. But why can I take this probability and by multiplying it by that get the probability that I get 25 ones and 25 zeros? Yes? Okay, so independence is coming in saying that this is the probability that I get 25 ones and then 25 zeros. If I got, okay, there's 2 things going on here. First of all, if I get 25 ones and then 25 zeros, is that mutually exclusive of getting 24 ones, a 0, a 1, and then 24 more ones? Are those disjoint outcomes? So if I consider the outcome 25 ones, then 25 zeros, and consider the outcome 24 ones, a 0, a 1, 24 more zeros, are those disjoint? What's the trial here? What's the experiment?
It has to be the order 0, 1, like the middle piece.
I'm feeling alone again. Okay, the experiment is to play the game 50 times in a row, right? Okay, so an outcome of the experiment is a sequence of zeros and ones. Yes? A sequence of 50 zeros and ones. If I have a sequence that starts with 25 ones, and I have a sequence that starts with 24 ones and then a 0, they're disjoint, right? Those are not the same outcome. If one happened, the other did not happen, right? Because they differ in what happened in the 25th draw. The outcome of a trial is 50 zeros and ones. If in those 50, the 25th is a 0, that is a different outcome from if in those 50, the 25th is a 1. They're disjoint. Right? If I get 24 ones, 0, 1, 24 zeros, that is a different outcome from getting 25 ones, 25 zeros. They're disjoint. Yes? Please? Okay, so they're disjoint. That's important because I want to add their probabilities. So because they're disjoint, I can find the probability that either of those things happens by adding their probabilities, right? Now, there's another thing that's going in, which is, well, what are those two probabilities? Well, we figured out that the first one has probability 1/2 to the 25th. You get, sorry, this should be 1/2 to the 50th. That should be confusing everybody. How about that? Excuse me. Wow. You let me get away with that for that long? Okay, 1/2 to the 50th. So what we had was we get 25 factors of 1/2 for the ones, and then 25 factors of 1/2 for the zeros. 1/2 to the 25th squared is 1/2 to the 50th, right? Okay, so the probability that I get 25 ones and then 25 zeros is 1/2 to the 50th. What's the chance that I get 24 ones, a 0, a 1, and 24 zeros? It's the same thing, right? I get a factor of 1/2 for all of the ones. There's 25 factors of 1/2. And then I get a factor of 1/2 for all of the zeros. That's 25 factors of 1/2. I still get 1/2 to the 50th. The order in which these things happen doesn't matter because the trials are independent, right? So every place that I posit a 1 in, I'm going to get a factor of 1/2. Every place that I posit a 0 in, I'm going to get a factor of 1/2. When I multiply them all together, I'm going to get 1/2 to the 50th. Okay, so the probability that I get 25 zeros and 25 ones is the sum of the probabilities that I get first 25 ones, then 25 zeros, first 25 zeros, then 25 ones, 1, 1, a 0, all of those different ways I can get 25 zeros and 25 ones. I have to add their probabilities. But they all have the same probability. So I get that same probability as many times as there are outcomes that contain 25 zeros and 25 ones. This is how many outcomes there are, disjoint outcomes that contain 25 zeros and 25 ones. So I can add all those probabilities together by just multiplying by how many there are, because they all have the same probability. Okay, so we've used the independence. We've used the fact that the probability of 1 and 0 are each 1/2. We've used the fact that these outcomes are disjoint. We've used some stuff on combinatorics on counting the number of ways there are of picking 25 of 50 places to have ones. So far, so good? Okay. Yes?
I thought you want 25 ones in a row and 25 zeros in a row. And so I thought we're doing like 25 ones, 25 zeros, or 25 zeros, 25 ones. Isn't that different?
So what we're looking for is what's the chance that in 50 plays of the game you win 25 times? Okay. You win 25 times.
So, and if it was in a row,
If we're 25 times in a row, it would be just that. Well, if it's the first 25 plays, and then losing the last 25, it would just be 1/2 to the 50th. Any particular string of zeros and ones that has this probability. Okay, but we're looking for all the strings of zeros and ones that contain 25 ones, exactly 25 ones. Okay. What's the chance that I get 5 ones and 45 zeros? So 5 ones and 45 zeros corresponds to winning the game 5 times in 50 plays, if in reality the chance of winning by switching is 1/2. So one way that I could do that is to win the first 5 times and then lose the last 45. The chance of that is 1/2 to the 50th. A different way of doing it is to lose the first, win the next 5, and then lose the last 44, whatever that is. The chance of that is 1/2 to the 50th. Right? Another way of doing it is to lose the first 45, win the last 5. The chance of that is 1/2 to the 50th. All those things are disjoint. How many of them are there? There's 50 choose 5 different ways of plonking down 5 ones and 45 zeros in 50 places. Yes? Okay, so in general, what do we find? We're going to introduce a symbol. We're going to let, let's say, X is the number of wins, in 50 plays of the game. And that's equal to the number of tickets labeled 1, whoops, in 50 draws. Right, in this model, those are the same thing. And let's ask, what is the probability that x is equal to little x in general? Okay, so capital X is this random thing. Little x is a placeholder. It's a dummy variable. And what we want to do is come up with a formula for this probability in terms of little x. So this is all if the box is this box. So if we're drawing from the box that has one ticket labeled 0, one ticket labeled 1, yes? It's a placeholder. It's like, in this case, we calculated this for x equals 25. We calculated this for x equals 5. What's the chance that when you do that, when you reach in this box 50 times, with replacement, pull out a ticket, replace it, stir it up again, what's the chance that you get this many tickets labeled 1, little x tickets labeled 1? This is how many you actually get. What's the chance that the number you actually get is equal to this number? Okay? So what is this? Any particular sequence of zeros and ones is going to have this chance, a half to the 50th, right? And then how many sequences are there that correspond to having this many ones? Okay? There are this many ways of getting x ones and 50 minus x zeros. Each of them has this probability. They're disjoint. So the probability that I get exactly x tickets labeled 1 is this, if I'm drawing from this box. So far, so good? Okay. If I'm drawing from the other box that has 2 tickets labeled 1 and 1 ticket labeled 0, I'm going to get a different answer, right? How's it going to differ? So now I'm considering the scenario that I have 1 ticket labeled 0, 2 tickets labeled 1. And I'm going to ask, what's the chance that I get 5 tickets labeled 1 and 45 tickets labeled 0 when I draw from this box 50 times with replacement? So I could get 5 tickets labeled 1 and 45 labeled 0 by getting 1, 1, 1, 1, 1. I could get 1s here, and then I could get, so this is 5 1s and 45 zeros. So what's the chance I get a ticket labeled 1 in the first draw? 2/3. What's the chance I get a ticket labeled 1 in the second draw, given that I got a ticket labeled 1 in the first draw? Still 2/3. Now what's the chance I get a ticket labeled 0 on the sixth draw, given that I got tickets labeled 1 on the first 5? 1/3. Okay, so what's the chance that I get 5 tickets labeled 1 and 45 tickets labeled 0 in this particular order? Right? I have 5 factors of 2/3 and 45 factors of 1/3. That's the chance I get them in this particular order. But now, if I'm just interested in getting 5 tickets labeled 1, but I don't care what order I got them in, I need to think about all the other orderings there are. How many other ways are there of plonking down 5 tickets labeled 1 and 45 labeled 0? it's still this factor of 50 choose 5, right? We have to pick, okay. And for each of those orderings, is the probability that I get that ordering the same? Right? So what if I said that I got a 0 and then 5 ones and then 44 zeros? What's the chance that that happens? Right? I get a third times 2/3 to the 5th times 1/3 to the 44th. Well, a third times a third to the 44th is a third to the 45th. And this is 2/3 to the 5th still. So the factors are in a different order, but their product is the same. Multiplication doesn't care about order, right? So every single one of those different orderings of 5 ones and 45 zeros has the same chance. And so the overall probability that I get 5 ones and 45 zeros is just this probability times the number of ways there are of doing that, because they all have the same chance. And that number of ways is 50 choose 5, right? 5 ways of picking, 50 choose 5 ways of picking which 5 trials resulted in tickets labeled 1. Which 5 draws resulted in tickets labeled 1. All right, so if the box is the other box, if the box is this box, what's the probability? What's the chance that when I reach in 50 times and pull out a ticket, what's the chance that I get little x tickets labeled 1 and 50 minus little x tickets labeled 0? So if that's the box, every time I ask for a ticket labeled 1, I'm going to get a factor of 2/3 in the probability, right? So 2/3 to the x. Every time I want a ticket labeled 0, I get a factor of 1/3. How many tickets labeled 0 do I have to get? 50 minus x. And then how many different ways are there of picking which of the 50 tickets, which of the 50 draws result in a ticket labeled 1? Okay. All right, so if reality is we're drawing from this box, the chance I get x tickets labeled 1 is this. And this is true for x equals 0, 1, on up to 50, right? And if I'm really drawing from this box, the chance I get x tickets labeled 1 is this for x equals 0, 1, on up to 50. So far, so good? You said hopefully? Yes?
For the 1, 0, 1, 1, how do you know that for the 50 choose x, that x is choosing the 1? Like that equation, how does that, like, in the other one, does that make sense?
Yes, I think. So basically, I need to count how many ways there are of arranging x 1s and 50 minus x 0s among 50 places. Okay. I could do that by saying which places get 1s, or I could do that by saying which places get 0s. Okay. If 50 choose x is equal to 50 choose 50 minus x. So picking where the 1s go, there's the same number of ways of doing that as picking where the 0s go. That okay. All right. So now let's generalize a little more. Let's forget about these particular boxes and think about drawing from a box that has a proportion p, a fraction p of tickets labeled 1. And the rest are labeled 0. So let's suppose that there are n tickets in all. N tickets in all. And what we have is n times P are labeled 1. And how many must be labeled 0 then? And again, we are reminded why it's bad for me to write on the board. Okay, so we've got this times np, this times n1 minus p. Okay, so a fraction p of the tickets are labeled 1, a fraction 1 minus p of the tickets are labeled 0. And now if we reach into this, then we're going to reach in n times and draw a ticket, random with replacement, independently. So independent draws. And let's let x be the number of tickets labeled 1 we get. In the n draws, and we want to know what's the probability that if we reach in little n times, we get little x tickets labeled 1, and the rest of the tickets are labeled 0. Can we generalize what we just generalized? Well, each time we try to get a ticket labeled 1, for each time we need to get a ticket labeled 1, we get a factor of p, right? What's the chance we get a ticket labeled 1 in the first draw? P. What's the chance we get a ticket labeled 1 in the second draw? P. What's the chance we get a ticket labeled 0 in the third draw? 1 minus p. The draws are all independent, right? So if I want to get n tickets, I want to get x tickets labeled 1. For each of those x tickets, I'm going to get a factor of p. And then I want to get little n minus x tickets labeled 0. For each of those, I get a factor of 1 minus p. Yes? And any particular configuration that has little x tickets labeled 1 and little n minus x tickets labeled 0 has the same probability. Each of those is going to have little x factors of p and little n minus little x factors of 1 minus p. So overall, what do I get? I'm going to get p to the x, 1 minus p to the n minus x. Okay, that's the chance of any particular sequence of outcomes that contains x tickets labeled 1 and n minus x tickets labeled 0. But then how many of such sequences are there? Yeah, little n, choose little x. Okay, I have to figure out which of the n draws results in a ticket labeled 1. The rest result in tickets labeled 0. Okay. Something that and this is true for x equals 0, 1, up to n. Right? We can't get fewer than 0 tickets labeled 1 in n draws, and we can't get more than n tickets labeled 1 in n draws. So this is called the binomial distribution. And it has two parameters. The fraction of tickets labeled 1, p, and the number of draws, n. So the parameters are little n and little p. Okay? You change the value of little n, you change the value of little p, you get a different distribution. It's drawing from a different box or drawing a different number of times. Little p tells you what box you're drawing from, tells you how many zeros and what fraction of zeros or fraction of ones. Little n tells you how many times you're drawing from the box. Yes? Well, if are we still counting how many tickets labeled 1 we get, or are we doing something else? Okay, so if the tickets are numbered 0 through 5, there's 1 of each. There's still 1/5 of the tickets are labeled 1. Right? The other ones, instead of being labeled, they're not all labeled 0, but they're labeled something other than 1. So P for that box would be 20%, because 20% of the tickets are labeled 1. If we're drawing independently with replacement, et cetera, we're drawing n times, it would just be p equal 20%. But the way we're going to generalize this more often is to think about, in this case, the number of tickets labeled 1 in the n draws is the same as the sum of the values on the tickets you see. Because every time you see a ticket labeled 1, that contributes 1 to the total. Every time you get a ticket labeled 0, it doesn't contribute anything. So the sum of the draws, in this case, is the same as the number of tickets labeled 1 that you get in all the draws. For an experiment where you're drawing from a box of numbered tickets numbered 0 through 5, the sum of the draws is no longer the number of tickets labeled 1, because you get a ticket labeled 5, it counts 5. Okay. We'll get there pretty soon. This all right so far? Okay. All right. Using this, suppose that I set my rule for deciding whether I'm drawing from this box or from this box by setting the threshold at 29. Let me see if I can't remember whether I set it as 29 or more or 29 or fewer. Okay, this isn't a bad way to lead in. All right, suppose that we're trying to decide between these two situations. A box that contains one ticket labeled 0, one ticket labeled 1, and a box that contains a ticket labeled 0 and a ticket labeled 5. And I reach into the box a bunch of times, and I pull out a ticket, and I look at what I get. Okay? If I ever get a ticket labeled 5, I know with certainty I must be drawing from this box. Right? If I ever get a ticket labeled 1, I know with certainty I must be drawing from this box. Okay? So a very reasonable rule would be, if you see a ticket labeled 5, conclude that it's this box. If you see a ticket labeled 1, conclude that it's this box. If all you ever see are tickets labeled 0, you might as well toss a coin to decide which one you're drawing from. You can't tell. Okay? So that rule is somehow saying, conclude that reality is whichever box makes it more likely to see what you saw. So if I see a ticket labeled 1, I conclude that reality is this box because that makes it more likely that I would see a ticket labeled 1 in the data. In fact, it makes it possible, and this makes it impossible. Right? Similarly, in this case, if I see a ticket labeled 5, that's more likely to happen if in reality I'm drawing from this box. Right? It's impossible to happen if I'm drawing from that box. We together on this? Okay, so a reasonable rule to sort of generalize this to cases where we're not talking about impossibilities versus possibilities, a reasonable rule for deciding between the case of drawing from this box or drawing from this box would be to say, I'm going to conclude that reality is whichever box would make it more likely to see what I actually saw. Okay, so if I'm more like, suppose I do the experiment, I draw 50 times, and I get 30 tickets labeled 1. If it's more likely to see 30 tickets labeled 1 drawing from this box than it is to see 30 tickets labeled 1 drawing from this box, I conclude that I'm drawing from that box. Okay? Similarly, if we kind of know that if I get 5 tickets labeled 1, that's more likely if I'm drawing from this box than if I'm drawing from this box. And if I get 48 tickets labeled 1, that's more likely to happen if I'm drawing from this box than if I'm drawing from this box. Okay? So what we want to do right now is kind of find the dividing line to sort of say, at what point does it become more likely to see that many tickets labeled 1 if you're drawing from this box than if you're drawing from this box? All right? So let's do the math. I think this might be easier to do on the board. This is the maximum likelihood principle, and it's one principle that people use for doing estimation. It's not the only one. All right, so let's suppose that I see X tickets labeled 1 when I do the experiment. I want to figure out which makes it more likely for that to happen, drawing from the box that has 50% zeros, 50% ones, or drawing from the box that has 1/3 zeros and 2/3 ones. Right? So I could look at the ratio of those two things. Right? So what's the probability? Introduce a new symbol here. Probability that X equals X on the assumption that we're drawing from this box. And I'm going to take the ratio of that to the probability that X equals X on the assumption that we're drawing from this box. Okay? And if this ratio is bigger than 1, then it's more likely to see what I saw if I'm drawing from this box. If this ratio is less than 1, it's more likely to see what I saw if I'm drawing from this box, right? Because this is less than this. Yes? No, it's just that one way you're going to conclude that, I mean, if this is bigger than 1, it means this was bigger probability than this. We can put the ratio either way. It's just that the rule is going to reverse, right? What we're looking for is which scenario makes the data more likely, drawing from this box or drawing from this box. But one way to express that is this is more likely than that if this ratio is bigger than 1. This is more likely than that if this ratio is less than 1. If I put the other one in the numerator, it would just flip. Okay. All right, so what is this probability? So if I'm drawing from this box, what's the chance that I get little x tickets labeled 1 in 50 draws? Well, this is 1/2 to the 50th times (50 choose x? Yep. Okay. And what's this one? Okay, can you see why I wanted to take the ratio? That's going to make life a little simpler. Yep. And this thing is just a constant. This doesn't depend on x, does it? Okay. So I basically just need to work with this to figure out what's going on. Moreover, can I simplify this a little bit? Okay, so what can I do? This is 1/2 to the 50th divided by, this is really 2 to the x times 1/3 to the 50th. Did everybody get that move? Right? This is 2 to the x times 1/3 to the x. 1/3 to the x times 1/3 to the 50 minus x is 1/3 to the 50th. Okay. So now, basically, I've got this whole thing is equal to 1/2 divided by 1/3 to the 50th divided by 2 to the x. So this is 2 to the minus x times 3/2 to the 50th. All right. So basically, if this number is less than 1, what do I conclude? Conclude I'm drawing from this box, right? If this number is bigger than 1, I conclude I'm drawing from this box. If I find the value of x where this thing just crosses 1, that's the threshold for deciding that I'm drawing from one box rather than the other. Does should this number go up or down as x gets bigger? Okay, this is 2 to the minus x. This is going to get smaller and smaller as x gets bigger. Does that make sense in terms of how we formulated the problem? The larger the number of tickets labeled 1, the less likely that is to happen if we're drawing from this box, the more likely it is to happen if we're drawing from this box, right? Okay, so it's going the right direction. All right, so if you take logs and solve this, you find that for x equals 0, 1, 2 on up to 29, the chance that you get that many tickets labeled 1 is larger if you're drawing from box 1 than if you're drawing from box 2. For x equal 30, 31, et cetera, on up to 50, the chance is larger if you're drawing from box 2 than if you're drawing from box 1. So the dividing line is 29. At 29 successes, 29 tickets labeled 1, you'd still conclude you were drawing from this box. At 30 or more, you'd conclude you're drawing from this box. Now, the rule can make mistakes, right? Because even if you're drawing from this box, it's possible that you get 30, 31, 32 on up to 50 tickets labeled 1. And if you're drawing from this box, it's still possible that you get 0, 1, 2 on up to 29. We could ask, if we're using this rule, what's the chance that we make each of those mistakes? So how do we do that? Well, what's the chance that if reality is that I'm drawing from this box, I erroneously conclude that I'm drawing from that box? Well, that's the chance that I get 30 tickets labeled 1 if I draw 50 times from this box, or 31 tickets labeled 1, or 32 tickets labeled 1, or 33 tickets labeled 1, on up to 50 tickets labeled 1. Right? What's the chance I get 30 or 31 or 32 or 33, et cetera? Those are all disjoint possibilities. If I get exactly 30 tickets labeled 1, I did not get exactly 31 tickets labeled 1, and so on. So I can add those chances to find the probability that I would erroneously conclude that I'm drawing from that box if in reality I'm drawing from this box. What is that? How is that in math? So the probability that I get 30, well, it's really the probability that x is greater than or equal to 30 on the assumption that I'm drawing from this box. And that's the chance that it's exactly 30 or exactly 31 or so forth and so on. And I can write that as a sum. That's the sum from, say, I was using x here, so let's go x equals 30 to 50 of a half to the 50th times 50 choose x. Yes? Messy thing to calculate. We have a computer to do it for us, which we'll use in a second. So this is the chance that I erroneously, that if I use this rule that says if you see 30 or more 1s, conclude that you're drawing from the box that has 2 1s and 1 0. If I use that rule, this is the chance that I erroneously conclude that I'm drawing from the box with 2 1s and 1 0, when in reality I'm drawing from this box. That's one kind of mistake. The other kind of mistake is the chance that I erroneously conclude I'm drawing from this box when in fact I'm drawing from the other. So that's the probability that x is less than or equal to 29 if in reality I'm drawing from this box. Okay? And that's going to be the sum from x equals 0 to 29 of 2/3 to the x, 1/3 to the 50 minus x times 50 choose x. Right? That's when x is 0, this is the chance that I don't get any tickets labeled 1 when I'm drawing from that box. When x is 1, it's the chance that I get exactly 1 ticket labeled 1. When x is 29, it's a chance that I get exactly 29 tickets labeled 1. Those are all the ways there are of getting 29 or fewer tickets labeled 1. So I've partitioned it into disjoint things, I can find the probability of the union by finding the sum of their probabilities. Yes?
And is the 30 and 29, these are all arbitrary numbers, right?
These numbers came from our, where did 29 and 30 come from? They came from the rule. We were using this maximum likelihood rule that says, conclude your drawing from box 2 if you get 30 or more tickets labeled 1. Conclude your drawing from box 1 if you get 29 or fewer tickets labeled 1. So now that we've got the rule, we can say, what's the chance the rule makes a mistake? Does that make sense? Okay. So we've got this binomial probability histogram somewhere in here. All right, so the histogram we were looking at before was an empirical histogram. We drew from a box a bunch of times and looked at how often the sum of the number of tickets labeled 1 in those draws was equal to a given number. This is now a different kind of histogram. The other was a histogram of data. This is a histogram of probabilities. So the area of each of these bins is what the binomial formula says it should be. So the area of the bin that's centered at 20 is a half to the 50th times 50 choose 20. Okay? It's the theoretical probability that this will occur, as opposed to looking at data and saying what fraction of the time did it occur. Does this make sense to everybody? Yes?
Can you go back and tell me how you got 29 as the cutoff point?
Sure. 29 was the point at which, if you see 29 tickets labeled 1, that's more likely to happen if this is the box you're drawing from than if this is the box you're drawing from. If you see 30 tickets labeled 1, that's more likely to happen if this is the box you're drawing from than if that's the box you're drawing from.
Okay, so if we're asked to find that number, we have to find the individual probability in both scenarios and see where one is bigger than the other?
Right, or work with the ratio or something like that. Sorry. Thanks. Okay, so this histogram is a probability histogram rather than a data histogram. The area of a bin is the probability of the outcome. The outcomes are all integers, right? If you're counting how many tickets labeled 1 you get, you can only get an integral number of tickets labeled 1. So the area of these bins have endpoints at half integer values. Right? There's really only one possible outcome in each bin. This bin that goes from 19.5 to 20.5 corresponds to the single outcome 20. That's the only possibility in that bin. Okay? And so this is now plotting the area of each of these bins is the probability of that outcome. The highlighted area here, the yellow, is the outcomes 30 or more tickets labeled 1, when in fact I'm drawing 50 times from a box of tickets that has 50% of the tickets labeled 1 and 50% of the tickets labeled 0. Right? So this is the chance that I would see 30 or more tickets labeled 1 if in reality I'm drawing from this box. So this sum corresponds to the yellow highlighted area. And this says that that's 10.1%. So the probability that I would erroneously conclude that I'm drawing from this box, if in reality I'm drawing from this box, using this rule that says if you see 30 or more, conclude you're drawing from this box, the chance I would make that mistake, if in reality I'm drawing from this box, is just over 10%. What's the chance that I would make the other mistake, that if in reality I'm drawing from this box, the chance that according to this rule I would erroneously conclude that I'm drawing from that box? That's, again, this chance that I see 29 or fewer tickets labeled 1. Okay, so what's going on here? Again, 50 draws, but now the chance of success in each draw, the fraction of tickets labeled 1 in the box is 2/3, right? 66.67%. And I'm asking, what's the chance that I get from no successes on up to 29.5, right? 29.5 is the endpoint of the bin that includes the outcome 29. So this is the chance that I see 30 or more. Sorry, this is the chance that I see 29 or fewer successes when I draw 50 times from this box. 29 or fewer tickets labeled 1 if I draw 50 times with replacement from this box. So that's this probability, and this says that that probability is 12.6%. So the chance of this was 10.1%, and this chance is 12.6%. Okay? No rule is perfect unless you're in a situation like that. One box has a ticket labeled 0 and a ticket labeled 5, and the other has a ticket labeled 1 and a ticket labeled 7. Then you could tell them apart based on one draw. But typically, if their contents are not completely disjoint, your rule is going to have some chance of making a mistake. And these are the two kinds of mistakes. And for this rule, those are the two chances. There was a hand up. I'm sorry. Yes?
So what does 1 or 100% minus 10.1 and minus 12.69 mean?
OK, question is, what does 100% minus 10.1 or 100% minus 12.6 mean? That 89.9% is the chance that if in reality you're drawing from this box, you correctly conclude that you're drawing from this box. And the, whatever this, 87.4% is the chance that if in reality you're drawing from this box, you correctly conclude that you're drawing from this box. Using that rule. Using the rule that says if you see 29 or fewer, say this. If you see 30 or more, say this. OK? All right. OK, let's do it. I need somebody to keep track of how many wins we get. I'm going to switch every time, because that's what we're looking at. And we're going to conclude that we're drawing from the box with 2 1s and 1 0 if we see 30 or more wins by switching in 50 tries. So, all right, so I'm going to guess, switch. There's 1 out of 1, 1 for 1, OK? Guess, switch, 2 for 2, 3 for 3, 3 for 4, 3 for 5, 4 for 6, 5 for 7, 5 for 8, 6 for 9. This is hard to say. 7 for 10, 8 for 11. Oops. 9 for 12. 9 for 13. 9 for 14. 9 for 15. 10 for 16. 11 for 17. 12 for 18. 13 for 19. 14 for 20. 15 for 21. 16 for 22. 17 for 23. 18 for 24. 19 for 25. 20 for 26. 21 for 27. 21 for 28. 21 for 29. 21 for 30. 22 for 31. 23 for 32. 24 for 33. 24 for 34. 25 for 35. 26 for 36. 27 for 37. 28 for 38. 29 for 39. 30 for 31. We can stop because even if we do the rest, we've got 30 or more. So we would conclude that we're drawing from box 2. Okay, so in this trial, we come to the right conclusion, right? Because we saw 30 or more wins in 50 plays of the game. That make sense? Okay. Let's talk a little more about the binomial distribution and things that do and don't have. So first of all, are there any questions before we wander backwards? Yes? if we had seen, if in the full 50 we had seen fewer than 30, we would have concluded that we're drawing from this box. And we know on theoretical grounds that that's the wrong answer, because we reasoned out last time that the chance of winning by switching is 2/3, so it's like the chance of getting a ticket labeled 1 when you draw from this box. Does that make sense? Yes.
Wait, in order to figure out 30 or 29 as your number, would you make the ratio equal to 1 and then solve for x? Or how would you?
Okay, how did we figure out 29 as the threshold? So the principle that we used this time, and it's not the only principle we could use, was to say, conclude that you're drawing from this box if you're more likely to see a certain number of successes drawing from this box versus this. Okay, so we concluded the box was whichever box made the chance of seeing what we saw biggest. If you just go through and solve that little problem, you can take logs and figure out where the threshold is. There's no number of successes that makes them exactly equal. At 29, this is more likely. At 30, this is more likely. Because it's discrete, it's got chunks. So now, that's not the only way we can make a rule. We could have a rule that says, okay, I want to be really, really careful not to make the mistake of concluding that this is what the world is like when it's really like this. I'm going to limit the chance of making that mistake to be at most, say, 5%. And then I'm willing to live with whatever chance that gives me of making the other mistake of concluding that the world is like this when it's really like this. So there are other principles I could use to decide to make a rule. The rule we just decided to use is called maximum likelihood. There's no, it's not coming down from on high as the only way to do this. And in fact, when we talk about hypothesis testing in a lot more detail later, our rule will typically be that we have one hypothesis that's privileged over the other called the null hypothesis, and we're going to pick a rule so that the chance that we erroneously reject the null hypothesis, erroneously conclude that the other thing is true, we're going to limit that probability to some threshold tolerance, like 5%, 10%, something like that. And then we'll take whatever we get. Now, suppose we wanted to make both of these chances smaller, the chance of this kind of error smaller and the chance of this kind of error smaller. What will we have to do? If I move the threshold up, I'll make this chance smaller, but I'll make this chance bigger. If I move the threshold down, I'll make this chance smaller, but this chance bigger. Yeah. Yeah, you have to play the game more times. Right? You need more data. You can't make the chance of both errors smaller without getting more data. That's the only way to make them both smaller. If you start moving the threshold around for 50 trials, you can make one of these smaller, but you make the other bigger. There's a nice characterization of, we'll talk about this more later, but type 1 and type 2 errors. So erroneously concluding that the world is this way when it's really this way versus erroneously concluding the world is this way when it's really that way. So that can characterize the difference between liberals and conservatives in terms of the kinds of errors they're more willing to make. This comes from a book called How to Tell the Liars from the Statisticians, if I'm remembering right. So the idea is that in one context, like conservatives are much more worried about giving benefits to somebody who doesn't deserve them than about not giving benefits to somebody who does deserve them. And liberals are concerned about the opposite. They're concerned about not giving benefits to somebody who deserves them and less concerned about accidentally giving benefits to somebody who doesn't deserve them. When it comes to punishment, it reverses. That the conservatives are more worried about not punishing somebody who deserves it than they are about punishing somebody who doesn't deserve it. And the liberals are more concerned about punishing somebody who doesn't deserve it than about not punishing somebody who does deserve it. Anyway. We okay at the moment? Other questions before we move backwards? All right, let's talk more about the binomial distribution. This is our first example of a probability distribution. So we have a bunch of possible outcomes in this case, 0 on up to 50. And we have an equation that tells us what the probability of each of those outcomes is. So in the general case that we were talking about, we have where we're drawing little n times from a box of tickets that has a fraction p of tickets labeled 1, the possible outcomes are 0, 1, 2, on up to n. We could get no tickets labeled 1 on up to little n tickets labeled 1. Right? And we're envisioning that we have np of those, and we have n 1 minus p of those, and we're drawing this many times with replacement, independent draws, so forth and so on. All right. If that's what we're doing, and our goal is to count how many tickets labeled 1 we get, which is the same as adding the values on the tickets we see. Right? The sum of the numbers on the tickets we get is equal to the number of tickets labeled 1 that we get. Is that clear to everybody? You add them together, you get a 1 for every ticket labeled 1, and a 0 for all the rest. That just counts how many tickets labeled 1 there are. So if we have x is equal to the number of tickets and that's also equal to the sum so if that's this is what we're counting. This is a random variable. Sorry, question? Can't read my handwriting? No, this is, capital N is how many tickets there are in the box. There's capital N tickets in all in the box. Little n is how many times we're drawing from the box. Okay? So population size is big N, sample size is little n. Okay? Thanks for asking that. Okay. Okay, so there's capital N tickets in the box, and all of them, a fraction p are labeled 1, and a fraction 1 minus p are labeled 0. We reach into the box little n times, pull out a ticket with replacement at random. Everything's independent. Then the probability that x is equal to little x is equal to p to the x, 1 minus p, little n minus little x, times little n, choose little x, for x equals 0, 1, on up to little n. Okay, this is the binomial probability distribution with parameters p and n. Yes?
Under what circumstances or like what types of data can't you use that for?
Okay, so that's exactly what I wanted to talk about. Thank you for asking the question. When does this make sense? What kinds of things have binomial probability distributions? What kinds of things don't? What are the essential ingredients? Well, we're drawing from a box of tickets where there's only 2 labels, 0 and 1. Okay? Now, some problems might start with a box with other labels, and we can convert it into this, but ultimately, 2 possible outcomes, success and failure, 0 and 1, true and false, something like that, binary outcomes, all right? We are counting something. We're counting how many successes there are. We're counting how many ones we get, something like that. Trials are independent. They have to be independent, all right? Every time we put the ticket back, we stir it up again, the trials are independent. And probability of success is the same in every trial. And we fix ahead of time how many times we're drawing, how many trials there are. So n has to be fixed ahead of time. P has to be fixed ahead of time. The trials have to be independent. And what we have to be doing is counting the number of successes, counting the number of tickets labeled 1, something like that. All right, so let's look at things that don't have a binomial distribution. Suppose I had a box of tickets labeled 0 and 1. So by the way, we're going to have boxes of tickets that are labeled 0 and 1. We're going to call 0, 1 boxes. So this is an example of a 0, 1 box. Okay. Suppose I have a box of tickets labeled 0 and 1. I reach into the box and I draw tickets at random with replacement until I get 3 tickets labeled 1 in a row. And then I ask, what's the probability that the total number of tickets I got labeled 1 was equal to 7? Can I use this formula to get that? Okay. Have I fixed n ahead of time? No. I'm not drawing a deterministic number of times. I'm not drawing a pre-specified number of times. I'm drawing a random number of times because I don't stop drawing until I get 3 tickets in a row labeled 1. Okay? So that wouldn't have a binomial distribution. What if I have a box that has 1,000 tickets, 500 labeled 1, 500 labeled 0, and I reach in and I pull out tickets without replacement, and I count how many tickets I get labeled 1 in 50 draws? That doesn't have a binomial distribution because the draws aren't independent. If I get a ticket labeled 1 the first time, I now know something else about the composition of the box has changed, right? It has one less ticket labeled 1 in it now. P isn't staying the same across trials. The trials are not independent. Okay? So if P is varying, if the trials aren't independent, if N isn't fixed ahead of time, you don't have a binomial distribution. If you're not counting the number of successes, counting the number of tickets labeled 1, counting something, then it doesn't have a binomial distribution. Let's look at a couple of examples here. There are a bunch of examples in the chapter. Okay, so, oh goodness, we're out of time. See you next time.